Hey guys, it is time for Mondays with Mike. My name is Mike and it's Monday, so it all makes sense. So today, first of all, it's good to see y'all here on a rainy Monday, as expected. Had some heavy downpours and probably will continue to see that today, probably tomorrow as well. I am off today because I worked Sunday night, so I'll be back on Tuesday. I have kind of a weird schedule. I'm going to be doing some mornings and some evenings coming up, but whichever shift we're on, we're all going to be watching the tropics for this week. And so we're going to be talking about that. So the first thing I want to do is I'm going to share my screen, and which I think is kind of fun. I like using these new tools. And so the first thing I want to show you is the agenda that I've set up for this discussion. And got to keep myself organized, right? So the first thing I'm going to show you is real quick. It's my favorite new cereal. You could probably guess what it is, right? And then we'll talk about some more interesting, serious stuff, including how we at Fox 26 monitor the tropics, why I think that you should ignore some of these viral Facebook posts that show a snapshot of a computer model forecast, and I'll explain why. We're going to talk about, and this is linked into that, we're going to talk about what a model ensemble is and why they should be trusted, I think, more than one single snapshot that somebody shares from a computer model. And this amazing, because I'm kind of like a little bit of a math nerd, not a little bit, I am a math nerd. And we're going to talk about, related to model ensembles, okay, a little bit of how they work, and I'm not an expert on them, but a little bit of how they work and how randomness can lead to something that's more accurate or reliable than actually taking specific measurements. How does that work? All right, well, let me go ahead and stop this share, and then I'm going to get to my web browser and talk about a few things. So here we go. Oh, wait a minute. I forgot my favorite cereal, right? I forgot about my favorite cereal. Wait, let me stop my share here. There we go. Here it is. Yep, you've probably guessed it. It is pumpkin spice, but I was at Target and I said, oh gosh, okay, so I've tried the Cheerios pumpkin spice. Now it's time to try Special K. And I will tell you, no offense to the folks at General Mills, you do a fine job with Cheerios, and I do like Cheerios. This tastes better. I will tell you that the pumpkin spice Cheerios definitely go more heavy on the spice, which I appreciate. You can definitely taste like cloves and allspice and stuff like that, but this goes a little heavier on the sweetness, and it's a little more pumpkin-y. I didn't really look at the ingredients to see if it actually has any pumpkin in it. It just says natural flavors. Oh yeah, it has spices and cinnamon and ginger and nutmeg and allspice. So yeah, this is legit. So I would recommend this if you like pumpkin spice. Probably not as much as I like it, but if you like pumpkin spice, I think you'll really like this. All right. So okay, so back to the agenda. Okay, so I've shared with you my favorite news cereal. Now I want to talk about how we monitor the tropics. So let me see if I can move. Can I move this to the bottom? Yeah, there we go. You know, the National Hurricane Center is, so you have NOAA. Okay, NOAA is the National Oceanic Atmospheric Administration. Actually, above them, you have the United States Department of Commerce. Okay, then under that, you have NOAA. And under that, you have a lot of different divisions. So you have the National Weather Service. And then under that umbrella, you have like the National Hurricane Center / Tropical Prediction Center. You have the Storm Prediction Center. They're the ones that issue tornado watches and severe thunderstorm watches and things like that. Then you have the Weather Prediction Center, and they come out with those maps for like excessive rain, and they forecast fronts and areas favored for heavy rain, heavy snow, stuff like that. And then there are a lot of other divisions under that. But this page that you're looking at right now is from the National Hurricane Center. So you can find it at nhc.noaa.gov, and they will display their 5-day tropical outlook. And if it's not on the page when you first, like the landing page looks like this, okay? And then they'll have some X's, and the X's are areas that they're a possible development. So if you click on 5-day tropical weather outlook, what you'll get is this. And you know, we went a long time with very little tropical activity. We did have one last week, which was that potential tropical cyclone number 4 that never developed. But right now, the tropics are finally starting to wake up. And by the way, when we talk about the tropics, it's sort of a blanket term that we use to talk about tropical activity in the Atlantic Ocean and everything connected to it. So Atlantic, Caribbean, Gulf of Mexico. I've seen some people kind of criticize the use of the tropics, because obviously the tropics is like a band of geography around the entire globe, you know, north and south of the equator. And so when we talk about the tropics, we're not talking about the whole world. We speaking to you, we're talking about the tropical Atlantic or the Atlantic basin. Now that we have that out of the way, we can see here that we have numerous areas that are highlighted in yellow, and those are the areas that have a smaller risk of developing. And then we have one spot here in the middle that is red, and that's an area that has a high likelihood for developing, and the Hurricane Center puts 50% for the next 48 hours and 80% over the next 5 days. And I'll show you that when we take a look at the computer models in a minute. So this is the area that's most likely to become our next tropical storm. The next name on the list is Danielle. And then the name after Danielle is Earl. And I remember Earl. It's funny, every time Earl comes up, because, you know, these names repeat every 6 years is the way it works. Unless they're retired, the name will recycle every 6 hurricane seasons. So Hurricane Earl was the very first hurricane that I sort of worked as a senior. Let's see, was I a senior? Yeah, I think I was a senior in college. So that was 1, 2, 3 Earls ago. So that was like 24 years ago. That was the first storm that I worked for WFSU television. And then, you know, shortly after that, I graduated. But anyway, so I always remember Hurricane Earl, and because it hit the Florida Panhandle, which is where Florida State University is. And it was like a total non-event, like nothing happened, but it was still fun to cover it. And I remember it was so silly. We were just broadcasting on WFSU, which is like the public television station. And I remember thinking when I went to Publix, to the grocery store, I'm like, I wonder if anybody's going to recognize me. I mean, of course they didn't. Nobody was watching. But anyway, yeah, so it was good times. So anyway, it was a long time ago. So this is one of the ways that we get a briefing. Like, you know, if you're going to come in and look at, the first thing we look at is going to be just going to the landing page of the Hurricane Center and saying, okay, well, what are they looking at? And if you want to really get deep into the weeds, you can go to this tropical weather discussion, where you'll get a really detailed description of, you know, all of the tropical waves that are present. And by the way, what is a tropical wave? It's just like a little area of low pressure, but it's like elongated. So it's like the winds go like this, boop, like that. It's like a little hump. And it's called a wave because it's a wave, right? They'll talk about this thing called the Monsoon Trough. I'll show you that here in a second. In the ITCZ, not ISCOVITZ, because that's my last name. And they talk about the Caribbean and the Gulf of Mexico and so forth. So, and then from here, if you're really nerdy, you can click on the surface analysis. It says 06 UTC. UTC is universal time. So it's also called Zulu time, or Z. And right now we are -5. So like 6 UTC would be 1 a.m. Central Daylight Time. So you can click on this, which is this really complicated looking analysis, right? And so this gives you a close-up view of what they're analyzing. So like this big L, for example, in the middle of the screen, that's the, and they even put the word gale on there, which means like tropical storm force winds, to warn ships and things like that. You know, that there's going to be very rough seas and high winds, so they may go around that. And then attached to that, so you're going to see here, if you look at where the L is and you look to the left, you see this thing that says ITCZ. And that's called the Intertropical Convergence Zone. And that's where the wind, the trade winds, are coming in like this on the top of it and coming in like this on the bottom of it. And so they kind of come together and they create this convergence zone where you have cloud cover. Now, the other line that's over here that's connected to this L, and that actually is also connected to this L, in Africa, that's called the Monsoon Trough. And really, I always used to call it just the Intertropical Convergence Zone. But the distinction that's made now is that you have winds on this side that are coming in like this. And then you actually have winds on this side that are coming in like this. So you have what is called cyclonic circulation or cyclonic shear on that monsoon trough. So that's why. So like if you were to go over here to this ITCZ, you would have winds coming in like this, and then winds coming in like this. So you don't have a spin, but you do have lift in the atmosphere. However, over here, you have winds coming in like this, and then you have a little bit of wind coming in like this. So that little difference, though, means that you'll get a spin. And so this is just what differentiates the monsoon trough, is what they call it, from the ITCZ. And by the way, that word monsoon, it has a lot of different meanings in weather. So it is confusing. Like we've talked about active monsoon in the Southwest. So like New Mexico's had a ton of rain this year. Arizona's had a lot of rain this year. That's called the Southwest monsoon. And it just means it's a seasonal, it's like a wet season, like a rainy season. It's kind of like the rainy season. You know, winds come in from the south and it makes everything wet. That's when they get the majority of their rains, like July, August, and maybe early September. And the same thing happens over in places like over in India and in Bangladesh, you know, places there in South Asia. They get an annual monsoon that comes in. Some people will also just call heavy rain a monsoon, or some people will even refer to like a tropical system as a monsoon. So the word is used a lot. So just be aware of that. You know, sometimes you hear the word monsoon, it can kind of mean different things, and I try to explain it whenever I use it. So, okay, so this is one of the ways that we take a look at what's happening in the tropics. And in fact, over here, if you look, whoops, I went over too far. If you look over here, you will see right in the middle of your screen, it says tropical wave. And then there's this up and down line. And that's the one that we're going to be talking about in a little bit more detail, which brings me to my next point, which is, remember, the next thing on the agenda was why you should ignore long-range model snapshots. And I'm going to explain why right now. Okay, so this is the latest run from the GFS, Global Forecast System. This is the American computer model. And I'm going to go ahead and zip forward in time. And you're going to see an area of low pressure. Well, you're going to see a big hurricane there in the Atlantic. But you're also going to see right there on the far left-hand side of the screen, you're going to see an area of low pressure there, this swirl with all kind of rain. So that is potentially what could be a tropical storm for the Labor Day weekend. This is actually Monday, Labor Day. So why am I showing you this? Well, let's go ahead and take a look at a model run from yesterday. Let's go back 24 hours ago. So right now we're at 6Z on August the 29th. Let's go back to 6Z on August the 28th. Okay. And let's look at what it was showing there. Okay. And look what it's showing there. Okay. You look, I hope y'all can see. Let me annotate on the screen here because I really want to make sure y'all see right here. Okay, I hope you can see that. But I mean, we're talking about right here. The model 24 hours ago was showing a 941 millibar low, which would basically be like a Cat 3 hurricane, maybe a Cat 4 hurricane, a very, very serious hurricane slamming into South Texas. And the model was predicting this on Sunday. Okay. Now, if we look at the latest, newest model run, what is it showing at that exact same time, Sunday night? Nothing. Okay. But what happens? Okay. What happens is that somebody has a Facebook page, like an enthusiast, which, you know what? I love weather enthusiasts. There's nothing wrong with that. But somebody will have a Facebook page where they will take a snapshot of that GFS model with a category 3 or 4 hurricane hitting Texas, and they will post that snapshot. And the people who see that will, oh my gosh, right? Well, the very next model run shows nothing even close to that. So let's talk about why that is. Why would the model change so much? Well, the reason is that what you're looking at right now, in fact, let me go ahead. I'm going to look at the newest model, which is 12Z, which actually just came out, which also is now showing nothing forming. What you're looking at right now is what's called a deterministic model. Deterministic. What does that mean? Well, deterministic means that you're trying to make a prediction of where something is going to be in the future, right? So let's say Justin Verlander, okay, is throwing a fastball, and you can calculate the weight of the baseball, and you can calculate how fast he's throwing it, and you could even measure, like, you know, how he's gripping it or whatever. And so based on that, you could use a computer model to predict where that ball is going to go. And you're probably going to get a very accurate result, right? I mean, you're going to know, okay, well, he's pointing it at the catcher, and basically it's going to be somewhere in the strike zone. You know what I mean? So that's pretty easy to predict. Okay. But now imagine predicting where a little piece of air is going to be, not in 1 second or 2 seconds from now, but 10 days from now. Okay. It sounds nearly impossible, and it is. Okay. So what you're looking at here, when you have, I mean, if you want to think about it like in baseball terms, it's also like, you know, you can predict where the pitch is going to be in 1 second, but let's say like there was no catcher there, or it was a wild pitch. Okay. The catcher missed it, you know, and it's a wild pitch. Well, then if I asked you to predict, okay, where exactly is the ball going to be after it bounces off the back wall and goes all over the place? It'd be a lot harder to point to where on the field the ball is going to be, right? Could be almost anywhere, you know, in that area back behind the, you know, it could fly in the dugout. It could bounce back to the infield. It could get stuck in the wall back behind the catcher. I mean, what I'm saying is, like, the longer out in time you go, these so-called deterministic models, if you're trying to predict exactly where that ball is going to be, it's nearly impossible, because you would need to know the most minute details about exactly how he threw the ball. If you were off by a little millimeter, your forecast would be completely wrong of where the ball is going to be. So that is absolutely exactly what happens with computer models. Okay, it's the exact same thing. We're trying to predict where this rain, where the wind, where the humidity is going to be. And just like a pitch, just like predicting, you know, Justin Verlander's fastball, when you're very, very close to the beginning, okay, which would be like 1 day out, 2 days out, 3 days out, you're going to be pretty close to being accurate. I mean, you're going to basically, if there's a tropical system, you're going to pretty much know where it is, within reason. However, just like a wild pitch, the farther out you go in time, the more prone to error, the more error there must be. Okay, it's not that the model's messing up, it's that the mathematics of it are such that unless your measurements at the very beginning are 100% exactly accurate down to 0.00000, the model is going to start to drift. Okay, so, which is exactly why you cannot look at this picture snapshot, which is September 4th, and say that's exactly where that low is going to be. Okay, so, which brings me to my next point, which is this concept of ensemble forecasting. What does that mean? Well, let's take a look at this. Okay, this I love. I absolutely love this. So what you're looking at right now, I'm going to make it full screen. What you're looking at right now is, this is amazing. So if you were to take a square piece of paper, okay, and if you were to, whoops, I don't want it to do this with pi. If you were to take a square piece of paper, okay, and if you were to draw a circle on it and start randomly, just randomly, like with your eyes closed, taking a pen and going random dots, okay? Maybe that wasn't the best. Come on, Mike. Random dots all over the page. You're not even looking, random dots. And let's say you put like 100 dots, okay? If you were to go back and count how many dots are inside the circle, and you were to compare it to how many dots are outside the circle, you can get a very, very good estimation of pi. Okay, so you know that pi is 3.1415. So like, for example, on the screen right now, it's showing like if you put raindrops or if you put little pencil marks on a piece of paper, after 1,200 drops, okay, 934 of them landed in the circle. And so if you divide 934 by the number of drops, you get 3.11, which is a very, very good estimate for pi. So Mike, what in the world does this have to do with computer modeling? Well, because what you're doing is you're actually using randomness, okay, which is these drops or these pencil marks or whatever you want to call them. This is randomness, but you're using it to predict an actual value of something. And actually, this turns out to be a far easier way of calculating pi than, measuring it. Like you would have to get like a tape measure, and like measure it all the way around. Or you do what they did like in the old days. You would break it into triangles like pie slices, pun intended, and then you calculate the value of every triangle, and that gives you an estimate for, you add it all up. But that's a hard way of doing it. This is an easier way of doing it. So Mike, what are you getting at here? Why are you boring me with this? Because several years ago, probably a couple of decades ago, actually, I don't remember the exact date. No, actually, this probably goes back to the 1950s, actually, when they started using computers to calculate the weather forecast. They came up with this concept of ensemble forecasting, which is not just used for weather. Okay, it's used for like predicting business cycles and the stock market and the spread of viruses. Like, I mean, it's used for a bunch of different things. And it's actually, if you want to look it up, because trust me, I'm not like a mathematical expert on this, so I wouldn't even pretend to go into a lot of detail about it. But if you want to look up what is called Monte Carlo simulation. And it's not like the Chevy Monte Carlo, which was a cool car. It's a Monte Carlo simulation. And anyway, what that means is you're adding randomness to the beginning of it. So if you were to just run one computer model, you would run into that problem that I just explained a couple minutes ago, which is you're taking this error at the beginning, like, not knowing exactly how fast Justin Verlander's pitch is. And then those errors are going to get compounded the farther out you go. You're never going to know where the ball is going to end up after it's a wild pitch. So, but if, okay, this is the neat part about it. If you were to introduce the randomness of those dots, okay, let's say instead of running one model of where the baseball is going to be, you ran 100 models. And with each model you added a random change to the location of the ball, a random change to how fast it's moving. And then you took the average of all those models, or you looked at the highest likelihood. Like if maybe the models all sort of lean toward a certain spot, you could say, well, it's more probable that it's going to land in that area. It's actually a much, much better way of forecasting than just relying on one model. So let me show you what I'm talking about here. So this is, I'm going to show you the GFS ensemble. Okay, so what this means is instead of just running the model once, like we were looking at before, they run a version of the model where they use this Monte Carlo randomness to run the model 30 times. So what I'm going to show you here is what's called the ensemble member representation. So I'm going to put this forward in time, and you're going to notice down there in the Caribbean, some of this yellow starting to show up. So that's low pressure. And as we look ahead in time here, so I'm going to fast forward this now to, this is now, let's see, let's go to Sunday afternoon. Okay, so you're going to see here a couple of different things. In the Gulf of Mexico here, you are going to see, here, let me circle here. I feel like I'm John Madden or something. So you're going to see here, this is a look at the ensemble members' prediction of low pressure. And I will tell you that they are in much better agreement today than they were a couple of days ago. And you can also, if you look really close, and I'm going to have to squint, you'll see little numbers on there, like one says 71 and one says 80 something. So if you were to look in there, that represents pressure levels. So like 971 or 980 or 990. So it is predicting a tropical storm or a hurricane. But obviously you're looking at it with the idea that we don't know exactly where it's going to be. Now, what's really interesting is if you look in the middle of your page, and I'm going to circle it right here, that's the hurricane that's expected to form in the Atlantic. And you will now see this huge spread among the ensemble. Okay. So what it's showing you is that pointing at that one model. Okay. And again, we'll go back to this real quick. And if I'm boring you, I'm sorry, because I think this is fascinating. Okay. If you go back to just what we call the deterministic model. Okay. Then you would look at this hurricane here and you would say, okay, that's where it is right there. Man, my drawing is terrible. You would say that's where it is right there. Here, let me use an arrow. You would say that's where the storm is right there. Okay, that's exactly where it's going to be on Sunday at noon. Well, maybe not so fast. Okay, because then if you go to the ensemble, okay, if we go to the ensemble, well, now all of a sudden, we're not so sure. Here's the ensemble member. Okay, well, now you're looking at, hold on a second. Now you're looking at this wide spread. I mean, look, you see all those red dots? Those are each one of the members of the ensemble. Okay, so the point that I'm getting at is that when somebody shares a snapshot image of something that looks very scary, if it's happening 1 day from now or 2 days from now or 3 days from now, yes, it's concerning. Okay. But if somebody shows something scary that's supposed to happen 10 days from now, and they're showing you like the GFS or the European model, what's called deterministic, not an ensemble, then it's total bunk. And they really don't understand what they're showing. And they're just trying to get clicks. It's like clickbait. It's absolutely wrong. So I just wanted to kind of plant that seed with you. And I know I got real wordy, and I know it's like, come on, Mike, like what are you doing to me here? But it's the reality of today. And the thing is, like, it's really hard to explain something like that on television, just in a 2-minute weathercast. But I just want you to think about that. Think about the idea that we do have models that we're going to show you that are deterministic, like when we show you the rainfall for the day today. Okay. It's short term. It's usually a pretty good forecast. But if you're trying to predict something that's happening in 7 days or 9 days or 11 days from now, you cannot look at a snapshot of a model and say, wow, that's going to be a giant hurricane, because the next model run is probably going to be completely different. But it will be more accurate if you watch the ensemble models, which we will share with you, by the way, when we show that spaghetti plot. Let me just, sorry, I'll let you go in a minute, but sorry. Let me just show you this one thing. And by the way, this website that I'm showing is called Tropical Tidbits. It is awesome. It's free to use, but the guy, Levi Cohen, who runs it, Cowan, you can get, like, put some money in the tip jar if you'd like to help him, because I'm sure it costs him a lot of money to put this together. But let me just show you this before I let you go. So let's go ahead and look at this area of investigation in the Atlantic. And what we'll show you is that you have these models, which are, this is a mixture of like the, like you'll see a red line there that says AVNI. Okay, that's an average of the GFS ensemble members. So anyway, this is one set of spaghetti plots. This is another one. Okay, this is a look. Each one of those lines represents a different member of the ensemble. Remember, I told you there were 30 runs that the GFS does of their ensemble. The black line is the average. So all those different runs, the black line is probably going to be the most accurate in the long run. Now we also have let's see, this is the Canadian model. Ensemble. So, and it gives you all the runs and then the average. So the bottom line is, guys, I just wanted to share with you why we sometimes get salty when we see people post these clickbait kind of maps. So, do you have a headache? I have a headache. Hopefully you, no, I don't have a headache, but hopefully you learned something. I know this was like a little bit of inside baseball, but that's what this segment is. That's what this segment is. So if you know anybody who may be interested, like maybe you have a son or daughter who is like wacko for weather and maybe is in high school and is taking physics or, you know, just college or whatever, they're just really interested in this stuff, or maybe they're 10 years old and they're just really interested in this stuff. Maybe pass this along to them, because I think it's interesting. I would have wanted to see something like this when I was 16, you know. So anyway, love you guys. Thanks so much for watching. Be sure to like the video and leave a polite comment or question, and maybe we'll get to it on a future Mondays with Mike. Take care.